All right, we are now ready to write a general formula for a Riemann sum using our new summation notation. So let's start with a picture. Let's suppose that I've got some curve, and I'm going to draw a fairly simple one here, just y equals f of x. And my goal is to figure out the area under this curve between x equal a and x equal b. So ultimately, I'd like to find the area under here, under the curve, between those two x values. I'm going to go ahead and use a right sum. So I'm going to go ahead and as I start to put rectangles in, I'm always going to determine the height of my rectangles by the right-hand side. Let's choose to build n rectangles. I don't want to commit yet to the exact number, so I'm just going to say in general, the number of rectangles will be n. That means that the width of each rectangle, I'm going to have to take this distance right in here and split it up into n equal parts. So I'm going to call this delta x, the width of the rectangles. Take this total distance, which would be b minus a, and divide it into the n equal parts to make n rectangles. All right, so I'm going to start from a here, and I'm going to move over one width, delta x, whatever it is. And so the value of x here is going to be a plus delta x. I'm going to use the y value at this point, right here, to kind of level myself off and create my first rectangle. I'm going to keep on doing that. I'm going to move over another place. So now instead of a plus 1 copy of delta x, I've gone over 2 delta x's. And again, I'm just going to use this y value on the graph at that point, level it off to create another rectangle. Let's draw one more. If I move over delta x again, I now have a plus 3 delta x's. And I've got my third rectangle built. I would continue to do this, right? I'd continue to build more and more and more rectangles until I end up at x equal b on the nth rectangle. So b is actually going to be a plus n delta x's. I've now built all n rectangles. And I'll do the same thing here. At that point, I would just be leveling off and making a rectangle, and there'd be a whole bunch more rectangles in between here. All right, so these rectangles are now an approximation for the area under my curve. And so if I could sum up the areas of all of these rectangles, I would have an approximation, a Riemann sum approximation, to the area underneath this curve. So let's see if we can do that. The area of just one rectangle. Area of a rectangle is base times height or length times width, however you want to think of it, right? And the base of each rectangle is just this little piece delta x. Now what about the heights? Let's think about those for a moment. To get the height of the first rectangle, I used this y value on my curve, and it's the y value for x equals a plus delta x. So this would be f of a plus delta x. Right? Using that same idea, the y value here, the height of the second rectangle, is the y value for a of 2, or f of a plus 2 delta x's. And then this one, of course, is the y value for a plus 3 delta x's. And so on and so on. This last one is f of b, but I could also write that as f of a plus n delta x's. So could I write that height in sort of a general way? Well, the height is always f of a plus, and then it's either 1 delta x, 2 delta x, 3 delta x, etc. So I'm just going to call this in general I times delta x, where I could be any number from 1 to n. All right, the total area is just going to be what I get when I add up the areas of all the individual rectangles. So we'll do that with our new sum notation. I'm actually going to write this f of a plus I delta x first times delta x. And again, like we just said, we have to do this when I is 1 and 2 and 3 up until I is n. So I goes from 1 to n. This formula is the formula for the Riemann sum. Provided, again, just as a reminder, we had this up at the top, but the delta x was b minus a over n. And again, this is the total area of all the rectangles. It's used as an approximation for the area under the curve, but since I used upper sums, I know that my approximation is actually going to be just a little bit too big, right? All right, let's go ahead and practice doing a problem, trying to approximate the area under a curve using this Riemann sum formula. So our goal is to try to find the area under the graph of f of x equals minus x squared plus 4x plus 5 between x equals 0 and x equals 3. We'll write the summation notation, the Riemann sum, and then we'll actually evaluate it for n equals 6 rectangles, 12 rectangles, 25 rectangles, and so on. So let's see. I'd like to go ahead and just see what this graph looks like. It's clearly an upside-down parabola, right? But let's get a feel for it. This is minus x squared plus 4x plus 5. And eventually, I just really want to concentrate on 0 to 3. Maybe I'll set my initial window to something like negative 2 to 5, just a little space around that. And I'll leave negative 10 to 10 for the y for now. Probably a good choice. So there's what that parabola looks like. And I really only want to go from x equals 0 to x equals 3. 3 looks like it's a bit past the vertex. So maybe about there. And of course, x equals 0 there. So my ultimate goal is to see if I could figure out this area. All right. We're going to do this with a Riemann sum. And I'm going to say that, again, my Riemann sum, the total area of all the rectangles, is the sum as I goes from 1 to n of f of a plus I delta x times delta x. That's the formula that we just figured out on the previous page. My delta x in this case, always b minus a over n. But I'm going to notice here I've got an a value of 0 and a b value of 3. So 3 minus 0 over n, or just 3 over n for the delta x. All right, let's start plugging stuff in. Our a is 0, plus I times our delta x is 3 over n. And that's multiplied by delta x, which is 3 over n. That's going to give me f of 3i over n times 3 over n. And if I plug this 3i over n into my function, I'm going to get minus, then 3i over n squared, plus 4 times 3i over n, plus 5, and then times that 3 over n. So I've got the sum as I goes from 1 to n of negative 9i squared over n squared plus 12i over n plus 5 times 3 over n. So we've got all of our kind of algebra setup done. Actually, one more step, sorry, I should probably distribute, and then I'll call my algebra setup done. Let's see, I would have negative 27i squared over n cubed plus 36i over n squared plus 15 over n. There we go. Now all of my algebra setup is done. At this stage, I'm going to try and evaluate this sum, and I'm going to do it with the help of my little chart here. I'll definitely be using those. So let's get ready for that. My first term, I would have negative 27 over n cubed. I'm going to pull that out front. Times the sum of I squared. Plus the second term, I'll do 36 over n squared times the sum of I. Plus, that's just a constant, so for now I'm just going to leave it the way it is. All right, so we've got negative 27 over n cubed times the sum of I squared from 1 to n. So I'm just going to put in this formula right here. n plus 1, 2n plus 1 over 6 plus 36 over n squared times the sum of I. And again, I'm just going to go ahead and put in my formula for the sum of I, n plus 1 over 2. By the way, these sum formulas are on your formulas list for exams and things as well. Plus, that 15 over n, there's no i's in there. So that's just treated as a constant. So the formula for a constant, take the constant times n. So the constant 15 over n times n. All right, we're back to algebra. What can I do? Dividing out a 3 gives me a 2 and a 9, and I can divide out one of the n's. So I'd have negative 9 And I'm just going to multiply those out. 2n squared plus 3n plus 1 over 2n squared plus 2 into 36 goes 18 times. Get rid of one of the n's. 18 times n plus 1 over n. Plus, of course, I can just get rid of those, 15. All right. You can leave it like that, or you can go one more step. I may have gone one more step, but it's not bad even the way it is. At this stage, I've got a sum that I could use to approximate the area under the curve for any number of rectangles. So what I'd like to do now is say, this is the approximation for the area under the curve. And let's just go ahead, and as the directions at the top of the page say, what if I used 6 rectangles? What if n is 6? Or what if it's 12 or 25 or so on? Let's make ourselves a little chart here. We wanted to use 6 rectangles, 12 rectangles, 25, 50, and 100. So I'm just going to plug these n values in to approximate the area for each one of those. And just to save us a little time, I think I've already got that in my calculator. I do. Yeah, I actually did go ahead and distribute. I made that negative 18. I had to use an x, so negative 18x squared minus 27x minus 9 and so on. But you will see that I've got everything in here. Okay. So in the table, if I want to use 6 rectangles, I'm getting 24.625 for the area. And again, that's the actual area of all 6 rectangles, but it's only an approximation to the area under the curve. Remember, I have a little extra space in my rectangles. What if I use 12 rectangles? 24.344 is now my area. If I use 25 rectangles, I'll get 24.173. If I use 50 rectangles, 24.088. And if I use 100 rectangles, 24.045. Okay. So, what do you think? Based on the pattern that you see in this table, do you think that you could approximate, or guess, I should say, the exact area under the curve? The more rectangles we use, the area seems to be getting closer and closer to what value? Looks to me like these numbers are all getting closer and closer to 24. So as the number of rectangles gets larger and larger, we could say it's approaching infinity. The area seems to be approaching 24. All right. So on the next page it says, is there actually a value of n that would let you find the exact area? And as we just said, essentially we have to let n approach infinity. We'd actually have to use an infinite number of rectangles to get the exact area. Although we can't truly do this, we know that we can do this as a limit, right? We know how to take a limit as n goes to infinity. And when we do this, we give our Riemann sum a new name. We say that if we take the limit of the Riemann sum as the number of rectangles approaches infinity, we have what's called the definite integral. We've got some new notation for this. Okay. So I'm going to summarize all this in this box. The exact area under the graph y equals f of x on the interval from a to b is going to be the limit as the number of rectangles goes to infinity. So I'd have the limit as n, the number of rectangles approaches infinity. And then I'm just going to put in that Riemann sum, right? This one right here. The sum as I goes from 1 to n of f of a plus I delta x times delta x. The new notation that we're going to give this is called the definite integral. And the notation looks like this. We put an integral sign, looks like a long S. And let's see, the area is between x equals a and x equals b, so we show that by putting in what we call limits of integration from a to b. It's the area under the graph of f of x. I'm going to put a dx here. And essentially what this is saying is this was the height of my rectangles. Here it is in the integral form. This was the base of my rectangles. And again, here it is in the integral form. Essentially, we use the dx instead of the delta x just to indicate that the base of the rectangles has to get smaller and smaller and smaller as I use more and more of them. So dx is like the infinitesimally small base. So I still have base times height. I still have the area of the rectangle represented in this definite integral notation. So this is the notation. At this point, this is the method we'll use to find it. So I'm going to go back to the problem that we just finished, and I'm going to say, when we left off finding the area under this curve between x equals 0 and x equals 3, we had gotten this area estimate, right? This whole big thing right here. We put that in the calculator and got some numerical values for it. But let's now actually say what would happen if we let n go to infinity. So I'm going to say the exact area would be the limit of all of this as n goes to infinity. I'm just going to write that down. It was that. All right, back to some limit skills. I think that to most easily see this limit, we probably should multiply this out, kind of like what I did when I put it in the calculator. So let me do one more algebra step here. I would have negative 18n squared minus 27n minus 9 over 2n squared plus 18n plus 18 over n plus 15. We've certainly done these kinds of limits before. You may remember that when we were writing out all of our steps, our technique was to divide the top and the bottom by the highest power of n. And we can certainly do that here. Or I'm also okay with you taking a shortcut and saying that when the highest power is the same top and bottom, we always get the ratio of the leading coefficients. So since there's so much going on in these problems, I'm just going to use that shortcut. By the way, these powers should always be the same if you've done these Riemann sum problems correctly. If they're not, look back and look for a mistake. So my limit's going to be negative 18 over 2 plus 18 over 1 plus 15, negative 9 plus 18 plus 15, 33 minus 9 is 24, which is exactly what we guessed it was going to be based on what we saw when we did the numerical limits. All right, we'll do a couple more examples, start to finish of this, in the next video, but now we've got all the ideas that we need to find the exact area under a curve.